Okay. Good evening, everyone. So, welcome to this live session on 6th April 2026, 5 p.m. So, if we observe previous 2 weeks, okay, so previously on week 6, so what we saw was the RH criteria, okay. So, RH criterion, and we also saw the root locus technique, okay. So, which both we'll be using to decide the stability of the systems. And week 7, that is previous week. So, basically, we saw the frequency response. So, frequency response. In this frequency response, we saw two things. So, one is Bode plots. So, another is Nyquist plots. Okay, so in both Bode plot and Nyquist plot also, we could see how to draw both these plots, and based upon the plots, we could decide the stability properties of the system. So now in this week, so we shift into a little different topic that is called as the design of controllers. So design of controllers. So using three things. So one is using two things. One is by using the root locus. Basically, we see this one in this week, and coming next week. So same design of controllers using this Bode plot. Okay, so now in this week we will concentrate on this design of controllers using based upon the root locus technique. Okay, so now let us shift to the week 6 content, particularly the root locus plot design. Am I audible?
Yes, sir, audible.
Yes. So I'm using the same example which I've taught in the week 6. So root locus, basically what we do. So given this closed loop system, where this closed loop system have the plant, controller C of S, and the reference R. So the feedback is H of S. This we call it is as the closed loop system. So here the controller C of S, it could be a proportional controller, derivative controller, integral controller, or combinations, or maybe a PID controller. Okay. So for this closed loop system, right, we know how to find the transfer function. So that is y by r. So output by reference input. So we could calculate this function, right? So based upon this function, we could also calculate the poles by equating the denominator of this transfer function d of s equal to 0. We could get the poles by equating d of s equal to 0. So those poles we call them as the closed loop poles. And based upon the poles location, we decide system is stable or not. Okay. So whenever this d of s having order greater than 3, it is not easy to find the poles easily. Okay. In such cases, okay. So we to decide the stability, we use the RH criteria. Also, so when we consider this controller, okay, so having different controllers, like when you say proportional controller, the proportional controller is represented with K. It means that your D of S having the constant K. Okay, so whenever you wanted to vary the K value from 0 to infinity, okay, so every time you have to find these poles. Okay, so what basically root locus technique says is it's a graphical technique. It will give you the locus of the closed loop poles. Okay, when you vary the K from 0 to infinity. Correct. So that's the root locus. Let us see, just quickly revise the steps we have followed in the previous week. Okay, so let's say this is the G of S, plant open loop plant transfer function. Okay, and assume that we have this feedback gain is 1. Okay, so let us say that we are using the proportional controller. in place of C of S. When you substitute, you'll get this closed loop transfer function as this way. Okay, so now this is your D of S. When you equate this one to 0, and if here you have this k, okay, you vary the k from 0 to infinity. And for every k, if you look at the poles on the S plane, you'll get the poles locus. Okay, so this root locus technique will give you the step-by-step process to without doing all without calculating the poles location for all these values of k from 0 to infinity. Okay, so root I hope this is clear. So in root locus, what we'll do is first step. Okay, so we'll put the closed loop transfer function in this events form, this form. Okay, so after keeping in this form, we consider this G2 of S here. Okay, that G2 of S expression for the given transfer function is this. So this is exactly equivalent to this. Okay, so that means that is equivalent to open loop transfer function. Okay, so basically uh, we draw the root locus by starting with open loop transfer function. Okay, so that is nothing but this expression. I hope this is clear. Okay, by drawing the root locus for the open loop transfer function, we get the poles location of the closed loop transfer function. Okay, so now here this is the open loop transfer function. This has poles 0, 2, and -1 plus or minus 2. So number of poles we have is 4. And the zeros is -3. Number of zeros is 1. So m is equal to 1, n is equal to 4. So that's the same example I'm revising for week 6. Okay. So then we look at the poles. So where we have poles, we have one at 0, another at 2, another at -1 plus z2. This is -1 minus z2 poles location, and 0 location at -3. That is our first step. Okay. Then second step is we have to find the starting and ending points of the root locus. Okay. So always starting is nothing but the open loop poles, ending is nothing but the open loop zeros. Okay. Here we have open loop poles are 4, open loop zeros are 1. Okay. It means that out of 4 poles, one pole will go to this 0. Okay, this step, and 3 poles will go to the infinity. So starting points are the poles, ending points are the zeros. Okay, that is second step. Okay, third step is real axis segments. So now you can see all these red cross marks and zeros. Okay, so when you start going from this side, okay, so when you start walking from this left to right. Okay, so at any point, if you see how many poles and zeros you have on your right side, okay, if that is equivalent to the odd number, then that will be part of the root locus. Suppose if you are here, right side, if you see only one pole is there, so this is part of root locus. If you are here, this is part of root locus. If you are here, that is not part. Okay, only this part will be if you are here on this part at any time, so this part will be on the root locus. Okay. Similarly, this part also on the root locus. This we call it is the real axis segment of the root locus. I hope there is no doubt on this. Okay. So root locus is these red strip points. Okay. Then what we do, we calculate so the asymptotes angles and asymptote centroid. Okay. So the asymptotes angle using this formula phi is equal to 180 plus alpha 360 by n minus m, where n is the number of poles, m is the number of zeros. Okay. Here n is nothing but the force, m is nothing but the 1. Here alpha is nothing but 0, 1, 2, 3, etc. n minus m minus 1, which is nothing but 2 here. It means that ultimately alpha is nothing but 0, 1, 2. This one. Okay, we get 3 values when you substitute alpha is equal to 0, 1, 2, 60, 180, and 300. Okay, so this is the we represents the angles. This is nothing but the centroid. So this is our centroid. Summation of the poles minus summation of zeros by n minus m. So you get 1. So that means that so this is the that one value. From there, you draw these three angles in these directions anti-clockwise. Is it clear? Any doubts? These we call them as the asymptotes. So these lines are called as the asymptotes. Okay. Then we calculate. So we said that. So the root locus will start at the poles and end at the zeros. Okay. So since it is starting at the poles, so we have something called as the departure angles. Since it is ending at the zeros, we have something called as the arrivals. Starting, we have departures. Ending, we have arrivals. So we have to calculate the angle of departures and angle of arrivals. Angle of departures are with respect to the poles. So we have totally four poles. Okay. We have four angles. Okay. Angle of departures are with respect to the zeros. We have one zero. Hence, we have one angle of arrival. Okay. So theta D1 is 0. Theta D2 is 180. Then theta D3 is 180. Theta uh, D4 is, sorry, theta D4 is 127.9. Okay. So this we have already seen how to do these calculations. Then angle of arrival. So theta, we have only one zero. So angle of arrival is 180. Hello? Yeah. Somebody was asking question.
Sir, can you
Yes. Yeah.
say in details angle of arrival, calculation of angle of arrival and departure?
Okay.
Uh,
You need explanation for that.
yeah, sir.
Okay. So basically what we do is, so let me show you that. Okay. So I'll show one calculation. Okay. So what are the poles and zeros we have? So we have one zero here. Sorry, one pole, one pole, one pole, one pole, and another zero. Okay. So let us call this is as P1, P2, P3, and P4. Okay. And this one is Z1. Okay. So now this is the equation for the angle of departure. Okay. So which says that Jay Patel, you can ask me uh, whatever you don't understand. Okay. So when I'm explaining, you can ask me because I'm reviewing this. I've solved the same question in the previous week also. You can watch that lecture for the same example. Because this week is dedicated to the design using root locus. That's why I'm just reviewing this, how to draw the root locus flat. Okay, so previous video is same example is available clearly. Okay, so now angle of departure I'm doing. Angle of departure is nothing but, yeah, I can send you that because this discourse does not having to upload the PDF. Okay, so you can do one thing, you can mail me after this live. I can share these lecture notes to you. Okay, handwritten notes. Yeah, sure. Okay, so now we are interested to calculate what is the angle of departure. Okay, angle of departure means the root locus is starting at the poles. Okay, it starts with which angle? That is the question. Okay, we use this formula. You can refer the professor videos for this formula, how this formula came. Okay, but we are using directly this formula. Okay, so now this formula you can see this theta zk. Okay, summation. It means that whatever all the zeros we have, those zeros, what is the angle they make with this P1? Angle they make with this P1. So that their summation is nothing but this term. Okay. Then similarly, what are all the other poles? Okay. They make the angle with this P1. So the theta di is theta D1 because we are calculating the theta D1. Okay, equal to 180. I hope this is clear. Okay, you can see that equation here. How many zeros we have? Only one zero. How many other poles we have? theta P2, theta P3, theta P4. Then minus theta D1 equal to 180. Is this equation clear? Any
Yes, sir.
doubts here?
Yes, sir. Clear, clear.
Yeah. So now what we do here is from this to this P1, draw the arrows from all other poles and zeros. Okay. So this is zero. This is the arrow. This is pole. This is the arrow. This is pole. This is the arrow. This is pole. This is the arrow. Is this clear? Now calculate the angles now. So how do we calculate angle? Always remember that this is how we calculate angle. Okay. So we have this x-axis, let us say, from here, the starting angle is like this. Okay, starting angle is like this. Always the angle increases by anti-clockwise direction. Okay, it means that this is zero. So this will be somewhere 45. This will be 90. So this will be 135. This will be 180, 270, and then 360. Is this clear? So this is how we do the calculations, angles. Okay, now you see, so this, tell me now. So this P2 vector, okay. So this is equivalent to what? This is equivalent to this vector. Am I sure? Am I correct? Yes or no? This vector is equivalent to this vector. So that is equivalent to 180. This is making an angle 180. Is it clear?
Yes, sir.
Yeah. Then similarly, if you see this one, it is making an angle 0 degrees, this one. Okay. Then P3, this is making an angle. So you have to take this x-axis. You have to shifting this x-axis. Then this is how you have to do the calculation with respect to the arrow. Okay. So that is nothing but what? This angle. Okay. 360 minus this angle. Am I correct?
Yes, sir.
Yeah. So how can you calculate this angle? So if you know this length and this length, we can take the tan inverse, correct?
Yes, sir.
So this location is -1 plus J2, correct? So it means that this is 2, this is 1, this is 1. Magnitude you have to take. Okay,
Yes, sir.
then that will be tan inverse of 2 by 1. Okay,
Okay,
so
okay.
that is
Yes,
how you have to do the calculation. Okay,
yes. Now I
then
got.
next,
Yes.
this the same thing again. So this angle and this angle summation will be equivalent to 360. So it means that you don't need to do that calculation. Directly you can substitute here 360. Okay, that is how the theta D1 will become 0 degrees. Clear?
Yes, sir. Clear.
In the same way, you have to do everything. Theta D2, theta D3, theta D4 also. Even theta Z1 also similar way. Only thing is that we have to use the different formula. Okay, same way you have to do. So this is the theta Z1. Draw the arrows from all other poles and zeros to this. Okay, then calculate the angles and substitute into this equation. Then you will get that. Okay, so once you have those, so uh, you can say that is how the root locus is entering. Sorry, uh, the root locus is the departuring or arriving at those poles and zeros. Okay, is this clear? Any doubt in this plot? Is this clear? Any doubt? Okay, let me draw it if you are having doubt. Okay, so I'll draw it again here. If you're having any doubt, you can ask me. So we have poles at 0, 2, -1 plus J2, -1 minus J2. This is -1, 0, 2. And we have 0 at 3. Is this clear? So this is the plus J2. This is minus J2. Is this step clear? Any doubt? Okay. Now we have already seen that these parts are the part of root locus. Is this step clear?
Yes, sir.
Any doubt? Okay. So now what we said was, okay, so the the centroid is at 1. Okay. The angles are plus 60, plus 300, plus 180. Okay. These are the asymptotes. Okay. Now we said that the root locus will start at open loop poles. Open loop poles means uh, these cross marks. Open loop 0 means this one. Okay. So, and end, they will end at open loop zeros. Okay. Now you can see these two poles, this first pole and this pole, they uh, they travel in opposite direction. They travel in opposite directions. They will hit here. Okay. So one will go in this direction. Okay. Another will go in this direction. Okay. That is first thing. Okay. Then, okay. Then, so these two poles, this is the P1, P2, okay, so P3 and then P4, okay. So now these two poles, P3 and P4, so they come like this, okay, and they go like this and reach here. One will go towards this zero, other will go towards zero at infinity. Is this clear? Any doubt? So that's how this one looks like, the root locus. Okay. The see starting points are the poles when k is equal to 0. Okay. Ending points are the poles when k is tending to infinity. Okay. So this is k tends to infinity. This also k tends to infinity. This is k tending to 0. Okay. So starting points are the k tending to 0. Ending points are the k tending to infinity. Is this clear? Any doubt you can see? Any doubt you can ask me. Okay, so if you simply follow these steps I have given in this notes, so you'll get this plot. Okay, so first you have to do this practice of drawing the root locus properly. Okay, now you could see here the at k is equal to 0, the root locus is starting at these poles. Okay, and as k is tending to infinity, it is reaching to the zeros at infinity and this zero. Okay. So, but unfortunately here you could see when k is tending to infinity, these poles, they are existing on the RHS side only. These two poles, zero pole and they tend to go, they tend to be in the RHS side only. So system is always unstable. Correct?
Yes, sir.
Yeah, with proportional controller, because k is here proportional controller, system is always unstable. Okay. From here we can decide that. Okay. So this is what we saw in the previous week 6. Okay, so drawing the root locus. Okay, so try to take simple functions. Okay, and try to draw the root locus. You will understand simply by following these steps. What are the steps? So all the steps are very clear. So first step is, so put your closed loop transfer function in the events form. Take this term, that is nothing but your open loop transfer function. Find the open loop zeros and poles. Okay. Then see what is the starting point and what is the ending point. That means how many you are going to check how many poles will end up at the existing zeros, how many poles will go towards to infinity. Okay. Then find the real axis. If you are working from the left side, right side onwards, going towards the left side, okay, you can decide these real axis segments, which are whether they are part of root locus or not. Okay, then find these asymptotes and centroid, then decide these asymptotes lines. Okay, then find these angle of departures and the angle of arrivals. Okay, then draw the root locus. Okay, only thing is that here you have these two things. So here we said that these two are coming here and hitting both and breaking away. So here this is nothing but break away. Okay, here these two are coming inside and becoming like break in. Okay, so how to calculate these two things? You will go through the examples and you will learn that. Okay, this is basically the overall procedure for drawing the root locus. Okay, so now by seeing here the as k is moving from 0 to infinity, we can see whether the system is stable or not. Okay, now this root locus plots we will use for designing the controllers. Okay, now we will get into that topic. Are there any quick queries? Are there any quick queries?
Sir, this type
Yeah,
of question will come in quiz too.
yeah,
Okay,
because
sir.
they'll be based upon the steps of the root locus. So
Okay,
it means that you should do the practice.
okay, sir.
Okay. Okay, now let us see this example. How to draw the control, how to do the controller design based upon the root locus. Okay, now I'll read this problem statement first. Okay, so you can see this. So uh, unity feedback. So that means h of s is 1. Okay, and the plant transfer function is g of s is given to you. Okay, we wanted to design the controller, okay, such that the step response of the closed loop system, zero steady state error. Okay, that means that so the design requirement, the ESS has to be 0 and peak overshoot should be 10%. 10% means what? 0.1. These are our two design requirements. Okay, we want our response should have the zero steady state error. Okay, and peak overshoot should be 10%. That means that peak overshoot not more than 10% means it should be less than a value of 0.1. Is this clear? Design requirements, any doubt? These are our aims. Okay. Now, question 1. Sketch the root locus of the proportional control system. That means control system of that C of S is K, and argue that it cannot meet these specifications. So with K only, we cannot meet these two specifications. Okay. Then propose suitable PI, PD, or PID controller, any one controller. Okay. So indicating that how adding these poles and zeros influence the root locus to meet these design requirements. Here in this case, we will try to design this PD controller. Okay. Then determine these controller parameters so that dominant poles satisfies these specifications, design specifications. Is this question clear? The question is that we have this plant, okay, and we are going for the closed loop system. Okay, closed loop system means how does it looks like? So closed loop system would looks like we have C of S, so we have Z, so here we'll get Y, here we have H, then here we have summing point. Okay, here we have R. Is it clear? So here the G is given to us. Okay, H is 1. Okay, now we have to design this controller C. We have to design this controller C. So what question is saying that first you draw the root locus with controller as C is equal to K. Okay, proportional controller. Okay, and verify that using proportional controller we cannot meet these requirements. Okay, then since we cannot meet with only proportional controller, try to take some other controller, either PI, PD, PID controller. Okay, so in our case we try with PD controller and see how adding poles and zeros what it will do to the root locus, whether it shifts to the right or shifts to the left. Okay, then finally determine these controller parameters so that they satisfy the specifications. If the question is clear, any doubt? Any doubts? Any doubts?
No, sir.
Yes. So this is our closed loop control system. Okay. So this is the closed loop control system. So we know how to calculate its transfer function, overall transfer function. Here given h is equal to 1. Okay. So this is the open loop transfer function. This is the open loop transfer function. Okay. The characteristic equation of closed loop transfer function will be like this: 1 plus GSHS, which we know already. Okay. So once you take that, this is your equation. This is your equation. Basically, in this equation, if you vary k from 0 to infinity, okay, you will get the poles movement. You will get the poles movement. You can do that manually. But we have already learned this root locus. Okay, you don't need to do that manually of k varying from 0 to infinity. Instead, if you simply follow the steps of the root locus, which we saw just before, so you will get the root locus plot. Yes or no? So for this open loop transfer function, if you follow the root locus steps, you will get the root locus plot. Okay, once you get the root locus plot, you can see uh, how root locus is varying for k varies from 0 to infinity. Using that, that will be our first question. Using that, we can answer the second and third questions. Okay, now this is our main thing: open loop transfer function. To Sorry, how k came. K is nothing but your proportional controller. Okay, here C is a controller. The controller C can be anything. So C can be a proportional controller, C can be a derivative controller, C can be a integral controller, PD controller, PI controller, PID controller, anything. Okay, now we are starting with the proportional controller, right? Proportional controller means simple constant. That's how the K came in. Okay, so now let us see. First step is to draw the root locus for this. Okay, 1 by S multiplied S plus 2, S plus 4. Okay, let us start with that. Okay, so first what we have is, so G of S, H of S equal to, let me write that. So GH I'll take, I'm removing this of S. 1 by S into S plus 2, S plus 4. To draw the root locus for it. What is our first step? Our first step is to put that in the events form. So assuming that I have already done. Okay. Next step is calculate the poles and zeros. What are the poles of this transfer function? S is equal to 0, S is equal to minus 2, S is equal to minus 4. Yes or no?
Yes, sir.
Right. So zeros, there are no zeros. Why? Because numerator is, we have only one. Okay. Now, if you see here, we have three poles, one no zeros. Okay. N minus M will be 3. N minus M will be 3. Okay. So now what are the starting points? So we have to decide starting and ending of root locus. What are the starting points? Starting points are the poles. What are the ending points? So since there are no zeros, what these three poles will do?
Infinity.
They'll go to,
It goes to
let us
infinity.
assume, zeros at infinity. Okay, so let us say that there are virtual zeros at infinity. That's why they are going to the infinity. Is this step clear? These are the starting and ending points. All the three poles, they go towards the infinity. Okay, so since they are going towards infinity, they will be having how many asymptotes? Three asymptotes, correct? Three asymptotes are three lines. They will guide three poles to the infinity. Okay, is this clear? That is nothing but this Q. Okay, so 0, 1, 2. These are three asymptotes. That is our alpha in that case. Okay, this is the equation for calculating the asymptotes. What are the angles? 60, 180, 300. Three asymptotes. Okay, then centroid. Centroid is as usual, summation of poles minus summation of zeros divided by n minus m. Summation of poles is 0, minus 2, minus 4. 0 is 0, minus 2. So centroid is located at minus 2. Okay, now let us see. Okay, so in this, what are the poles we have? Poles we have is at 0, at minus 2, at minus 4. Is this clear? Any doubt? These are the poles. Any doubt in this?
No, sir.
Okay. Then you can see the centroid is at minus 2. Sigma centroid is at minus 2 and asymptotes are 3 asymptotes 60, 180, 300. So centroid at minus 2. Okay. Asymptotes are these lines. These lines. So one is 60. It goes like this. Another is 300. It goes like this. Another is 180. It goes like this. Clear? So they actually show the direction to these poles. Okay. Now you see, so here this pole, minus 2 pole and 0 pole, right? Before that, the real axis segments. Okay. If you start here, okay, if you walking towards left, okay. So if you are anywhere on this line and see right side, you will see only one pole, correct? If you are anywhere on this line, here till here, if you see right side, you will see only one pole. Am I correct?
Yes, sir. Correct.
So hence this will be part of the root locus. If you are here anywhere on this, if you are here anywhere on this, and if you see right side, you will see two poles, which is a even number. That's why this blue is not part of the root locus. Okay. If you are here anywhere on this line, and if you see the right side, you will see three poles, which is the odd number. Hence, this red strip is the part of root locus. It means that only these two red strips are part of root locus on the real axis. Is this clear?
Yes, sir. Clear.
Yes. Now, what this minus 2 pole and 0 pole they will do is, okay, so they travel. The 0 will travel, okay, and minus 2 will travel. Okay, they will travel till this middle point. Till this middle point, okay, like this in this direction. Okay, then at that point they will hit, and one pole will go in this direction by following that 60 asymptote. Another pole will follow in this direction by following that 300-degree asymptote. Okay, all then this pole at minus 4, it will follow the asymptote. We have already drawn this asymptote of minus 180 degrees. It will follow in this direction. So you can see now all the poles, they are going towards infinity. Am I correct? So only these red strips are part of the root locus. Is there any doubt? Only these red strips, red lines in this picture are the part of the root locus. Any doubt?
No, sir.
Yeah. So now this is the question. Okay, here. The minus 2 pole and 0 pole, they are coming and hitting here. We are saying that that is break away because they are going away. Okay, that we will calculate by using this equation. Okay, at that point, the k, the derivative of k becomes 0 with respect to the s. Okay, what we do is, so dk by ds equal to 0. That equation we will try to solve it. How do we do that? We have already this equation. So the characteristic equation. From this equation, we will find the expression for k, which is nothing but minus of s cube plus 6s square plus 8s. This one. This equation. Is this clear?
Yes, sir.
So
Clear.
to that, we take the derivative dk by ds and equate it to 0. We get the s value. We solve that equation, we get the s value. Okay. So this s value having two things, but plus we have one value, minus we have one value. Okay. So the S1 and S2 minus 0.846 minus 3.14154. Okay. Now substitute these S1 and S2 in this expression again. Okay. So one you will get is 3.079. Another you will get is minus 3.079. Okay. So, but always here we are looking for k varying from 0 to infinity. So always we expect our k to be positive. Hence, this is the meaningful value. Okay. K is greater than 0. Okay. So at that stage, what is the corresponding k? Corresponding s will be minus 0.846 and corresponding k is 3.794. This is the combination. Is this clear? So that means what? What is this point? Now tell me, what is this point? That point is nothing but what?
That is
Minus
minus 8. Yes.
0.846. Okay, that is the point where these minus 2 and 0 poles, they break away. Okay. And at that point, what is the K value?
3.079.
Yes, exactly. So 3.079. That is how you can find. Clear? Any doubts in this? Okay, this is our root locus. First question done. Okay, now, so we have to check. Okay, what are our design requirements? The design requirements are the steady state error should be 0 and the peak overshoot has to be less than or equal to 0.1. Now we will check whether we are meeting this root locus. We can be able to find that. Can we fix that k value? Okay, let us check that. Okay, here also one more point. Here you see that the root locus is crossing this j omega here, correct? Here. So to find at what value of k, what is the k value here? Okay, the root locus is crossing. And what is that omega value here? The root locus is crossing at this point. If you wanted to calculate that, what you do is consider the same characteristic polynomial of your closed loop system. Okay, so substitute s is equal to j omega because it is the j omega axis. Okay, so you know already that omega square is equal to -1. Use this one. Okay, substitute into this equation. So you will get the k value as what? Sorry. So these are the two things. Okay. So this is the equation. In this equation, okay. So equate your real axis. What is the real axis? Minus 6 omega square. This one plus k equal to 0. Okay. So that gives us k is equal to 6 omega square. Then imaginary part to 0. So omega multiplied omega square plus 8. Okay. So this gives, okay. So if you check here, this gives two things. Omega is equal to 0 and omega square plus 8 equal to 0. Okay. Omega is equal to 0 is very trivial case. We don't consider that. Okay. Omega square plus 8 equal to 0. So we get omega as 2.82. Okay. Then substitute into this equation. K is equal to 6 omega square. You get K as 48. Okay. So these are the two things. S is equal to plus or minus j 2.2 root 2, 2 root 2, and K is equal to 48. What are these two things? So this is the frequency. The root locus is crossing the j omega axis. At that time, the K value is what? 48. Is this clear? Any doubt? Is this clear? Any queries in this? So here you are trying to know the root locus is crossing this j omega axis. What is the omega here and what is the k value here? That you got them as omega as 2 root 2, k value as 48. Any queries in this? So this is what you need to do. So take the characteristic polynomial, substitute s is equal to j omega equate real and imaginary part to 0, then solve for k and omega. Those are the two things. Okay. Now, so the first step is over now. Okay. Now we have to check. So we have drawn the root locus with the proportional control by taking only k in place of c. Okay. So let us see the steady state error. This is the equation we already know for the steady state error. Okay. So that is ESS equal to limit to s tending to 0 s E of s. Okay. S multiplied. This is the E of s expression. Okay. R of s is, let's say, 1 by s. We are applying the unit step. Okay. The G of s, H of s expression is this. If you do the calculation, what is the thing you are getting? 0. So E of ESS is satisfied for any value of k. Yes or no?
Yes, sir.
Yeah, for any value of k, because it is 0, error is 0. Steady state error. For any value of k, ESS is satisfied. Now let us check for the peak overshoot, whether this is less than or equal to 0.1 or 10%. Okay. Now let us see here. This is the equation for the peak overshoot for the second order systems. E power minus zeta pi by root over 1 minus zeta square multiplied 100. Okay. So our design requirement is it should be less than or equal to 0.1. Okay. So equate this one to 0.1. Okay. Take the natural logarithm on the both the sides. Okay. Find zeta value. Okay. You got zeta as 0.591. 0.591. Okay. That is the zeta minimum, which will give you the overshoot of 10%. Which will give you the overshoot of 10%. Okay. So to meet this requirement, our zeta minimum should be 0.91, 0.591. Okay. Now, along with that, if you see the settling time for 2% tolerance in our, you might have seen this formula in the time domain analysis. The
Yes, sir.
settling time TS. Okay, 4 by beta already we know. Let us see what is this omega n value. That means what? We are saying that to meet this uh, peak overshoot, we this peak overshoot requirement, we need to have this zeta as 0.591. And we are also interested to check what is the settling time, okay, with these values. Okay, so for that, what we do again is, so consider this equation S cube. You can see that S cube plus 6s square plus 8s plus k. This is the characteristic equation. Okay. And if you consider the standard cubic representation like this, so standard second order multiplied S plus P3, another pole, that will give you standard cubic representation. Now compare 1 and 2. Compare 1 and 2. Okay. If you match the terms, okay, you'll get P3 as minus 0.4, minus 4.57. If you match the terms, it means, so you multiply this entire thing, match the coefficients. Here we have 1, here we have 1. Okay, something like that. Okay, if you compare everything, you will get P3 as minus 0.5 of 4.57. 4.57. Okay, so once you have that, okay, so you can calculate. You can calculate. So the dominant poles. Okay, so dominant poles are like this. You can calculate the dominant poles. Okay, so here you have already minus 0.715. Dominant poles are nothing but the poles of this system which are near to 0, which are nearer to the origin. Okay, so the dominant poles are this way. Okay, they have this form, minus zeta omega n plus or minus omega n root over 1 minus zeta square. The dominant poles are equivalent to the poles of the second order system. Any doubt in this? Anyone? Any
Sir,
doubts? Yes.
from we have to calculate omega n from by comparing
Yes.
1 and 2.
No, no, no. If you compare the coefficients of 1 and 2, Okay, you will get value of P3.
Okay.
Okay, so once you have P3, okay, so for K is equal to 0, okay, you will get two more poles, these poles. Sorry, for K is equal to this value. Okay, you will get two more poles. Okay, so
Okay.
these poles, if you compare here, okay,
Okay.
minus
Okay.
zeta omega n is 0.715. That you
Yes.
are considering here, then you are calculating the omega n. You don't need to
Yes.
calculate. Directly we can substitute here for calculating the this TS. Okay, settling time. What
Yes.
is the
Yes.
settling time here? We are getting 5.6. Okay, settling time we are getting as 5.6. Okay, 5.6 means it is uh, very slow. It is taking longer time to settle down. Okay, here what we saw finally. So the K value. So initially for any K, we can able to meet steady state error. So for to meet this, we need zeta of this much. Okay. So for this, uh, we for this zeta, we are getting a settling time of 5.6. Means your system is meeting the overshoot requirement, but taking longer time. It is taking the longer time. Okay. So that's what it means. Is this clear? Any doubts? Any doubts? Okay.
So
So
then,
taking longer time.
if
Yeah.
TS is high, then we can say that it
Ah,
is uh, not slower, faster than.
it is not faster. Yes, that is the problem. Okay.
Okay.
Now that is with the first question only. Okay. Here our conclusion is the settling time is not very high. The settling time is very high. It means that system is reaching to the uh, final state very slow. Okay. Now what we do is because of that we are going for the question B. Okay. What is question B? What is the other controller you will propose? Okay. So here we try to propose this PD controller. Okay, you can see the PD controller. Basically, in PD controller, what we do is we take C of S like this. We take C of S like this. So what does it mean? Okay, here we're adding a zero of minus A. Right? PD controller, we always add a zero. Okay, so this zero, what it does is it pulls the root locus to the left. It pulls the root locus to the left. So root locus is moving left means what? It is
Stable.
reaching the, yeah, it is, we are pushing towards the stable region. Okay. So
Yes.
ultimately, it reaches the equilibrium point fastly. So that is nothing but increasing the, decreasing the TS. Or you can say that very fast. Okay. In this, what we do is we'll try to place this zero near the plant pole. What is this plant pole? We have S is equal to -2. Okay. We place this A value at -2. So hence what will happen? This is what will happen. Okay. Here what does it becomes? This term and this term gets cancelled. So 1 0 is getting cancelled with one pole. This we call it is as a pole zero cancellation. Pole zero cancellation. Okay. Because of pole zero cancellation, we have Kc by S multiplied S plus 4. Okay. So this is nothing but second order dominant behavior. So that we can shape easily. Okay. Now using this, our aim is can we reduce this? Can we reduce this settling time? Okay. Now in place of the open loop controls, open loop transfer function, we will use only this instead of this. Okay. So now again do the same thing. Okay. So overshoot should be this much, our zeta is this. Okay, we are looking for the faster response. Now here you should see. So from this, okay, zeta omega n is 2. Then omega n is 3.384. Then poles becomes these things. Then imaginary is this. Okay. The desired poles will be like this: -2 plus or minus Z 2.73. Okay. So if you choose your uh, real pole at this, okay, you'll have a faster response. You'll have a faster response. What we are trying to do here is we have changed our open loop transfer function. From there, we are calculating our zeta omega n. Okay, then we are trying to say that what are our poles, desired dominant poles location. Okay, so finally you can see this. So this is the C of S. Okay, so the modified characteristic equation with this new C of S. Okay, so again compare these two. Okay, so if you match all the terms, you'll get P3, KC, and A. Finally, this is your controller expression. With this controller expression, these are the dominant poles. Okay, -2 plus or minus J 2.73. With these dominant poles, okay, so you'll have the damping ratio, you'll have overshoot this much. Now the settling time is 2 seconds. Previously, the settling time is 5.6 seconds. Correct? Right?
Yes, sir,
Now
correct.
the summary. Okay. So initially what we did, we have drawn the root locus with proportional controller. Okay. To meet requirements of ESS equal to 0 and overshoot is 10%. Okay. These two we are meeting, but the settling time is little higher. Okay. Settling time is little higher. For that reason, okay, we proposed PD controller to reduce the settling time without change, without disturbing these two. Okay, so this is the proportional derivative controller expression we got. These are the dominant poles. Now it results in reducing the settling time to 5.67 seconds to 2 seconds. Okay, so that's the reality. Now, still what happened, this is what the PD controller we are getting. Okay, but in reality, when we try to implement it, because controller means it is the electronic component. Okay, so there are some practical issues comes into picture. Okay, to handle those practical issues, what we do is we will design something called as the compensator. Okay, so no, we don't go with just this expression. Instead, we will try to add some pole also. Okay, in this case, we call that is as the lead compensator. Okay, so this is what the meaning of designing the controller using root locus. So can you ask any questions? So let me go through that quickly, what we have done. Okay, so first we have this G of S, the plant transfer function. Okay, and we have unity feedback. First our step is, A step is to consider only the proportional controller, draw the root locus, and decide whether we met these two design requirements. Okay, for that reason, so once we check these design requirements, so check whether we met those design requirements or not. If you don't met, so propose one of these three controllers, PI, PD, PID. In our case, we went for the PD controller. Then finally find the controller parameters. Okay, is this question clear? Any doubt?
Sir, how we recognize that we have to use PI or PID or PD?
Yes, yes. So basically, that depends upon the here. What is why did I went for PD? Can you tell me why did I went for PD? Here the settling time it is more, correct?
Yes, sir.
So that is why we went for PD. So that I'll tell you in the next example. The lead lag. So it is like what I do is uh, we'll go in two steps. I'll just come to that point. We'll go in two steps. So here these are the questions. First, we have to consider the proportional controller. Okay. Then draw the root locus. So the steps are same for drawing the root locus by considering the proportional controller. This is our root locus. Okay. So based upon the root locus, okay. So we have to answer. We have to answer this question. Okay. So then we said that okay, this is satisfying the uh, for any k, whereas the MP, so we will get the zeta as like this. Okay. So zeta should be like this. So then we are checking the settling time. Okay. The settling time we are getting is very high value. Okay. So for this k, we are getting settling time of 5.6 seconds. This k is equal to 6.69. It will give you a overshoot of 10% and a settling time of 5.6 seconds. Hence, we decide that so the settling time we can be able to uh, achieve, but sorry, the overshoot we could be able to achieve, but settling time is more. Hence, we are going for the PD controller. Okay, the question is why we are going for PD controller, PI controller, or PID controller. Okay, that we'll discuss deeply in the next lecture. Okay, here my intention is to how we are using the root locus for the design problems. Okay, now what we do is after we decided PD controller, this is the expression for CS. Okay, our job is to design what is KC, what is A value. That is our that is our point. So we choose our A nearest to the system pole. This system pole, we are choosing that 0. Okay. Then we get this open loop transfer function. Then we are checking with this open loop transfer function, can we able to reduce our TS? That's what we are doing here. Okay. So we get our desired dominant poles. Okay. So this way. Then finally, uh, we could calculate using the desired dominant poles, we could calculate our P3, KC, and A like this, which will give us the settling time of 2 seconds. Okay, so you have to go step by step procedure. Okay, so this is possible when once you draw properly the root locus, and from root locus you need to keep checking the k values. Okay, so you should use the MATLAB also sometime, particularly for the. I think you have this week written assignment, correct?
Yes,
That
sir.
written experiment, particularly on the lead lag design. Okay. Now coming to your question, how do we choose the whether we are going for the PD, PID, etc. Okay. So basically there are two things. Okay. Steady state error. Okay, next is the transient response. Okay, so steady state error and then transient response. Okay, so improving, improve the steady state error and improve the transient response. Okay, so what generally we do in the next class, I'll go with only one example. Okay, what I do is we'll take one example. Okay, we will start with the integral controller. Okay, we'll start with the integral controller and try to show how this integral controller will improve the steady state error, will improve the or reduce the steady state error. Okay, improve in controlling the steady state error. Then from here, we will go to PI. There we will exactly see why we are going for the PI. Then we will go to something called as the lag compensator. Okay, similarly, here we will start with the derivative controller, which improves the transient response. Transient response means what? Basically, the settling time. Okay, no, sorry. Transient response means see the MP, peak overshoot. Steady state response means settling time. Okay, reducing settling time means improving the steady state error. Reducing peak overshoot means improving the transient response. Okay, from this we will see why we are going for the PD controller. Okay, then from this we will see the lag compensator, lead compensators. Okay, so combining these two, okay, so we will have the PID controller, then lead lag. Okay, lead lag compensator. So, uh, Sir has already explained one full example, okay, in the video lectures. Please go through that. And also in the coming Wednesday's live, I'll also take one full example other than the one explained in the video lectures. And I'll go like this, in this way. Start with integral controller. We will see what is happening and then go to PID and then go to lag compensator and design. Okay. Similarly, we will start with derivative, then PD, then lead compensator. Finally, this is obvious. You can understand the lead lag easily once you understand these two. Is this clear? So here we tried something, this one in this previous example. Okay, so the basic necessity here is to use the root locus. So once you are adding the poles or once you are adding the zeros, so you have to observe how the root locus is shifting right or left. Okay, is this clear? Any queries? Yeah, somebody was asking a doubt. Yeah, do we have week 8 in the syllabus? Yes. So 5, 6, 7, 8 is
Sir,
two.
this week
Yeah, yes.
it is a little tough to solve this week with week 8 questions.
No. The exam pattern is different. Exam pattern is 1 hour only. Okay, so you will get such kind of questions only, not this much lengthy questions.
But in the previous session, ma'am has confirmed that week 8 will not be in the quiz too, I think.
No, week 8 in the sense you will see this flavor. Okay, not this kind of this much of bigger examples. Okay, basically the week 8 and week 9 we are giving these assignment problems. Okay, you have to submit this assignment. Okay, you got the
Sir,
point? Yes.
for MATLAB, what we have to do? I
Uh,
uh,
Sorry.
for MATLAB,
See, MATLAB, it is like, suppose what is the purpose of MATLAB with respect to the root locus? If we just give R locus, okay, of your numerator coefficient and denominator coefficient of your open loop transfer function, it will directly give you the root locus plot. Is this clear?
sir, we have to install MATLAB, then download MATLAB.
No, not needed. You can use the online MATLAB also. Online free version is already available.
Okay, then in week 8 graded assignment, we have to
That is up to
check
you.
only.
That is up to you.
Only check. We have to check only, or we have to submit this MATLAB.
You have to submit the code also, the MATLAB code also. MATLAB code and your PDF should have the pictures of root locus, etc.
Okay.
Okay,
So
so
I can't
using
upload
MATLAB
it.
one advantage is that if you use this command. Okay, it will directly give you the root locus plot. You don't need to follow all those steps. Okay, once you see the root locus plot, you can judge whether the system is stable or not as k is tending from 0 to infinity. Then you can see that example. So particularly here, so what we have been doing, so at this level, okay, we just added only proportional controller and we got this root locus. Okay, this root locus will give you some idea of about whether we are meeting the design requirements or not. After that, what you are doing, you are adding a PD controller. You are adding a PD controller. Okay, what this PD controller is doing, so you will add a zero. Once you add a zero, the it will pull the root locus to the left, which ultimately reduces this steady state time, settling time. Okay, so the question is how much you need to pull. That is your design part. Is that clear? How much you need to pull, that depends upon what are your design requirements and how much you need to pull. These parameters P3, KCA, those things you have to calculate based upon your design parameters. Okay, so reduce your TS from 5.6 onwards. These are our design parameters. Okay, so that is practical experiment. Is this clear? Is this clear? The syllabus for quiz 2 is 4 to 8, but 8, if you see, these are design experiments. We have already given the assignment. Okay, so but you should know what is happening with the PD controller, what is happening with PID controller. So you'll get short answers. You'll get to short answer questions, not like to draw complete root locus and answer all these things. No, because quiz is only for 1 hour. Okay, so literally the syllabus is 5, 6, 7, 8 modules. Okay, any queries? Any queries? Okay, so if there are no queries, let us go for this surprise test. Okay, so everyone take this one, take this example.
Hello, sir.
Yes, yes, yes,
Huh. Before going to the surprise test, I want to
yes,
convey that
yes.
in this control engineering, it is very difficult to solve the question or understand the concept what both instructor are telling us. And we are not providing any additional resources so that we can understand from there, that is from the G or PH solution, or in the quiz one also there is no mock test or something has released. So
Mock
can
test.
you do? Yeah, it is very big, very become very difficult to understand how to deal with the questions. And in the lecture or in the session also,
Huh.
uh, there is no question solving, more on focus on that, which comes in the quiz too. It is very messy type. I am not understanding what about this concept. And basically if you do